from improper integrals. Just a little review. We can marry all this stuff so nicely. Remember, if I did the integral from 1 to infinity of f of x dx was greater than or equal to the integral from 1 to infinity of g of x dx, and let's say that g of x dx diverged, right? Didn't this imply that the integral from 1 to infinity of f of x dx must also diverge? Similarly, if the integral from 1 to infinity of f of x dx was less than or equal to the integral from 1 to infinity of g of x dx, and this guy converged. I got a bunch of values that are less than, right? Now remember, you got to be real careful here. This guy's got to converge, all right? And so that takes care of things like positive functions and things of that nature. Then doesn't this imply that the integral from 1 to infinity of f of x dx must also converge? And this was called the comparison test. Comparison test for integrals. Well, by virtue of the fact that we just married a bunch of positive, a bunch of positive series to these integrals, guess what we have? We now have a comparison test for series. This is called the comparison test series, which is what we're about to come up with. All right, we just have to rewrite this up using series instead of integrals. So suppose a sub n is less than or equal to b sub n for all n, right? Now that's going to get a little bit wiggly, and I'll redefine that in class. But for now, let's just assume that it's for every n, okay? And this is important. A sub n and b sub n are series with positive terms. We got to keep it positive, because if we by virtue of the fact that if a sub n is less than b sub n, but I blast down towards negative infinity, then clearly I'm going to diverge in the negative direction. All right, so you got to think about why we have to call these things positive. All right, our series with positive terms. All right, so here's what we got. We got a sub n, b sub n. They're positive. A sub n is less than or equal to b sub n for all values, okay? Then what can we imply? Well, if the sum as n goes from 1 to infinity of b sub n converges, then what does that imply about the sum as n goes from 1 to infinity of a sub n? Well, if this guy converges, and this guy's always got positive terms, but all the values are less than or equal to the values in b sub n, then this guy has to converge. It's just an extension of the integral test, or of the comparison test for integrals, the integral comparison test. If the sum as opposed to the integral, see how you mix that up, a little mixed metaphor mathematically speaking, it's a lot of n's. If the sum as n goes from 1 to infinity of a sub n diverges, guess what? Guess what you got? If I take the sum as n goes from 1 to infinity of b sub n, I mean, you can see how it writes itself, right? B sub n is always bigger than a sub n, greater than or equal to. A sub n diverges. Guess what b sub n's got to do, or the series with b sub n. I get a little bit cavalier with the use of saying b sub n versus the series of b sub n. You got to yell at me about that from time to time. Let me give you an example. Remember back with comparison tests for integrals when I said we're doing lawyer math, we have to present our cases. All right, we're going to do that. We're going to do that right now, okay? So I want to talk about this series. I want to talk about the series as, let's see, as n goes from 1 to infinity of 1 over 2 to the n minus 1. Let's keep it as simple as possible. No, I'm sorry, 1 over 2 to the n plus 1. All right? Now, first and foremost, look at it. Is it one of our home bases? Is it the harmonic? Well, clearly no. Is it geometric? It kind of smells geometric, but I get this +1 action going on here, so I can't really make the argument that it's geometric. Crap. Okay, well, is it a p series? Does it look like one of these guys? 1 over n to the p. Does it look like one of those? No. Crap. However, it does kind of smell geometric, doesn't it? So let's think about something for a sec. What do I know about 1 over 2 to the n and 1 over 2 to the n plus 1? Do you agree that 1 over 2 to the n is always greater, when n goes from 1 to infinity, of course, is always greater than 1 over 2 to the n plus 1? There's no doubt about it, right? Now think about that. Make sure the denominator is always bigger. Therefore, the value of the fraction is always less. Now, doesn't this imply that the sum, as n goes from 1 to infinity, of 1 over 2 to the n is always going to be greater than the sum, as n goes from 1 to infinity, of 1 over 2 to the n plus 1. Isn't that correct? So we've just made an argument. All right. So here's what we do. Since I know the sum, as n goes from 1 to infinity, of 1 over 2 to the n is geometric. So here's what we're going to do. We're going to write this up. We're going to go, it's convergent because r is equal to 1/2, or you could say r is less than, absolute r is less than 1. So remember, if I had to write this thing out, it would be 1/2 plus 1/4 plus 1/8, etc., right? So r equals 1/2. R is less than, absolute r is less than 1. Either one of those counts as a justification. So since this guy converges, and here's where it gets lawyerly, by the comparison test, which you can just say by CT, the sum, as n goes from 1 to infinity, of 1 over 2 to the n plus 1 converges, and I'm done. Looks very much like I did back when I was proving convergence of integrals, of improper integrals, using the convergence test. They look, they smell the same. Okay? All right, so we're going to get into some nastier ones like that, but it's so useful. All right, another example of that would be like, let's see, n equals 1 to infinity of, let's go this guy. How about 1 over n squared plus, because this will lead nicely into what's called the limit comparison test, which is awesome, 1 over n squared plus 3n plus 2. How about that guy? Now, hopefully you can see this. We're going to make an argument. What does this smell like? Oh, crap, it's not a geometric. It's not a p. Ooh, kind of looks like a p series. If this part right here were missing, if this were gone, that'd be a simple p series, wouldn't it? All right. Well, what do you notice? Let's do it. Well, let's keep it in blue. Let's look at an observation. Okay, we're going to say, look at 1 over n squared and 1 over n squared plus 3n plus 2. Right? Well, what do you notice? So long as n is between 1 and infinity, what happens? This guy is always less than this guy. You see the argument? You can see where this happens, or see what happens here? This implies that the sum, as n goes from 1 to infinity, of 1 over n squared plus 3n plus 2 is less than, we don't even need less than, do we? According to these guys, let's see, where are we? We need less than or equal to. So I could even say less than or equal to the sum, as n goes from 1 to infinity, of 1 over n squared, and the sum, as n goes from 1 to infinity, of 1 over n squared converges. Why? Because p equals 2. Or you could just as easily write p is greater than 1. This implies that my sum, I'm sorry, you guys, let's go over here. This implies that my sum, as n goes from 1 to infinity, of 1 over n squared plus 3n plus 2, that was it, wasn't it? 3n plus 2, converges by comparison test. Works the exact same way as the comparison test for integrals work. That's the coolest part. Now, the most important thing is that we meet the assumptions, and the assumptions are that we always have positive terms. Now, I always have students where they're like, wait, Ripley, what if I don't have positive terms. Well, let me show you something real quick. This is sort of an aside. What if I have the sum as n goes from 1 to infinity of 1 over, let's go n squared minus, let's see, I got to make sure that I don't want, minus 1.5. Now look at that. What happens? Well, when I plug n equals 1 in, do you notice that I get a negative term? So I know that a sub 1 is equal to 1 over negative 1/2, right? Which is negative 2. A sub 2 is equal to 1 over 4 minus 3/2, which is what? 1 over 5/2. Is that right? Let's see. 8/2 minus 5/2, all by that, which is 2/5. And then from n equals 2 on, I'm always going to have positive values, right? Well, we don't worry about that because there's a finite number of negative values. So as long as you're removing a finite number of negative values, you can treat this thing as though it's always got positive values. And the way in which you do that, you would simply write this as, let's do equals. This is just a little numerical trick. This just equals negative 2 plus the sum as n goes from 2 to infinity of 1 over n squared minus 1.5, or 3/2. Okay? See how that works? And all I did was remove a finite number of negative terms, and then from this point hence, this guy right here is always greater than, is always greater than 0, not greater than or equal to. All right? I got another awesomely powerful test for you. And it's the last test in the section. And it's called the limit comparison test. I love this one. And it works really well with the one that we just did. There are some tests, these tests overlap. In other words, tests aren't mutually exclusive. You can use different tests to test for whether or not we diverge or we converge, and they better give you the same conclusion, otherwise we're screwed. All right? So I'm going to talk about the limit comparison test.